Now, if the particle is going in a circle, then this length, let me call this as S and this is R. Now this relation, I think you know from class 6th, that S is equal to R into theta. And mind you, the theta here would be in radian. You studied the sector and the length of the sector, and you studied there that you might have studied with a variable L. This is R, and if this is L, this is theta, then L is R into theta. You know this relation already. So this is a constraint that if a particle is moving in a circle, then the distance on the circumference that it has covered, that will be given by this relation, R into theta. Theta is the angle which it has covered. So the angle which it has covered, that would be dependent on the distance that it has covered on the circumference and vice versa. But this relation will always hold. It comes from geometry, which you already know. Okay. Okay, now I'm going to differentiate these two sides. So I'm going to get ds by dt is equal to r into d theta by dt. And d theta by dt we already know is the angular velocity, the rate with which the angular position is changing. So this is r into omega. Omega will be representing angular velocity with. Okay, now ds by dt is a rate of change of distance, the rate of change of distance on the circumference. So this is actually the velocity with which the particle is moving on circumference. So this is the linear velocity. Actually, this is the distance by which the particle is covering. This is the velocity with which the particle is covering the distance on the circumference. This is the linear velocity. If you cut the circle from here and make it straight, so actually the particle was moving in a straight line. If you think of it like that, if you cut the circle from here and make it a straight line, so the particle is covering some distance round and round the circle. So this thing ds by dt is the velocity with which the particle is covering some distance. So this is the linear velocity of the particle, or in this case we'll be calling it the tangential velocity of the particle, because the particle is always moving on the circle. So the displacement will always be perpendicular to the radius. We'll discuss after some time, but for now ds by dt is the linear velocity, or we can call it the tangential velocity. So I'm writing it just as v, because this is the velocity with which the particle is covering the distance. So v is equal to r into omega. This is the relation that is coming from geometry. This is the constraint that the particle has to follow if it is moving in a circle. So omega is the rate of change of angle. So rate of change of angle obviously will depend upon the velocity with which it is covering the distance on the circumference and vice versa. And that velocity should be proportional to r, because you see, if you have a smaller circle and you have a larger circle, so if a particle starts from a position and goes all the way around in the circle and comes back, so it will cover a distance of 2 pi, angular distance of 2 pi in both the cases. So this velocity, and they do in the same time, so this velocity will remain the same because they have covered the same distance of 2 pi in the same time. But the linear velocity will be much higher for the larger circle, because the distance that the particle has to actually travel around the circle will be much larger in this case, and it will be actually proportional to radius, because the distance is 2 pi r circumference. So it is proportional to radius. So it should come like that. The velocity with which it is covering the distance on circumference should be proportional to the radius. And you have this relation. This is the important relation. This is the first thing that we are learning in circular motion, that the velocity, tangential velocity or the linear velocity, is r times angular velocity. It's coming from a simple geometrical relation, and I hope you must also have got a good feel now. So this is the first relation on which the rest of the chapter will be built. Very important. and very basic. V is equal to r omega, the linear or tangential velocity is equal to r times the angular velocity. Now, if we again differentiate it, then dv by dt is going to give you the acceleration, right? No problem with this. dv by dt is acceleration, and I'm calling it as at, meaning this is a tangential acceleration, meaning the acceleration with which the velocity is increasing along the circumference. Now, when a particle is moving along the circumference, the direction keeps on changing, and the velocity is always tangential, and tangent are always perpendicular to the radius. So when a particle is at this point and it is undergoing a uniform, or it is undergoing a circular motion, then at this point the velocity is towards the tangent. At this point again the velocity is towards the tangent. It has to be. If you remember the constraint motion that we studied and the definition of circular motion. Circular motion, the definition is the distance between the center and the particle does not change. The distance will not change if there is no velocity along this line joining the center and the particle. If there is some velocity along this line, there will be some distance traveled along this line. And if the distance has to remain the same, that is the constraint, then we have done these things before, that the velocity component along this line should be 0. Velocity component along this line will only be 0 if all the velocity is perpendicular to this line. That means the velocity should always be perpendicular to the radius. That means the velocity should be tangential. So this velocity that we are talking about, the velocity with which the particle is moving round and round in the circle, that is the tangential velocity. The rate of change of that velocity is the acceleration, and I'm calling that as tangential acceleration, at. Right? So you differentiate the left hand side with respect to time and you're going to get at, and right hand side r is a constant. So r will remain as it is, and you're going to differentiate omega, and d omega by dt, the rate of change of angular velocity is angular acceleration, which we represent by alpha. So you have another relation, that tangential acceleration is r times angular acceleration. Okay, so far so good. Things are easy. You understand? Two important relations to begin with. V is equal to r omega and at is equal to r alpha. At is the tangential acceleration, alpha is the angular acceleration, v is the tangential velocity, omega is the angular velocity. All right.